So, last time we were talking about bonding in hydrogen, and this involves, as we said, the MO theory picture is going to not only give us the identity of a bond and where it comes from. The bond in hydrogen comes from end-on-end overlap of two 1s orbitals, one on each hydrogen, and it looks like this, and that's a sigma bond. But the other thing we need to add that you may not be used to thinking about is that MO theory requires whenever you bring two atomic orbitals together and mix them or overlap them to make a bond, you also make an anti-bonding orbital. I'm not getting emotional, my voice is just, those anti-bonding orbitals, boy, it gets you right here. The anti-bonding orbital comes from the destructive interference or out-of-phase combination of the two orbitals. And why you have to do that is just embedded in the math of MO theory. It turns out both of those orbitals are solutions to the Schrodinger equation for this molecule. It's just that one is lower in energy than the other. And so when you put electrons in these orbitals, they fill the bonding orbital. The anti-bonding orbital is empty. And there you go. Now you can think of the anti-bonding orbital as the place where additional electrons would go if we had any, or you can think of it as a higher energy state, a higher order harmonic, a higher order waveform that the electron could adopt if it received a certain amount of energy. And of course, most of the time for that to happen, the electron would need to absorb a photon of light. So this energy difference between the bonding orbital and the anti-bonding orbital is the amount of energy it would take to promote an electron, okay? And you could calculate that out. You could calculate it out exactly if you knew this energy gap, exactly what frequency of photon you would need to promote an electron from the filled orbital to the empty orbital. Yeah?
So I have two questions. First of all, should we become comfortable with being able to draw this energy diagram?
So drawing an energy diagram like this, yeah, you should become somewhat comfortable with that. What else?
And the second question was, if I understand it correctly, by adding a photon and promoting an electron, that can bring a bond?
Exactly. So the prediction is if you have a photon of just the right frequency to promote one of these electrons up to the higher energy anti-bonding orbital, that would break the bond. Now here's the reason why. The bonding orbital is lower in energy than the two original 1s atomic orbitals. That makes sense because that's why bonds form. We talked last time about a reason why the bonding orbital is lower in energy. There's two reasons. One is a potential energy reason, one is a kinetic energy reason. The potential energy reason is that the electrons in the bonding orbital get to spend most of their time between the two nuclei, and proximity to the nucleus is lower in energy because the nucleus is positively charged, the electrons are negatively charged. The kinetic energy reason, though, is also interesting. You'll have to accept this on faith, but the math proves it. Electrons that are spread out have lower kinetic energy than electrons that are highly localized. And in a bond, you get to spread out over more space than if you're on a single atom. So atoms in a bond have both lower potential energy and kinetic energy than they would if they were on an isolated atom. Yes? Sure. So the question, and I'm going to answer that in just a second. But what I wanted to say is that the bonding orbital is lower in energy than the starting point by a certain amount. But the anti-bonding orbital energy, we'll call that delta E star, because it's the difference between the starting orbitals and the sigma star. That is actually bigger in magnitude. We'll use absolute value signs to indicate that we're in magnitude. Sorry, that's a little bit of mathematical scrupulosity on my part. This energy gap is bigger than this energy gap. Okay, so when you promote an electron to the higher anti-bonding orbital, it not only cancels out the bond, but it makes it worse than it would be if the bond weren't there, and that's what makes the molecule fly apart. So we're going to see in general, when you populate an antibonding orbital, either by promoting an electron up to the higher level or by filling the antibonding orbital completely, you break a bond. That's a really useful thing to know in OChem. We're going to use that to explain how reactions happen all the time. I'm going to say that, I'm going to say that one more time. When you fill an antibonding orbital, you break the corresponding bond. Yeah? Is bond strength only to the level of the atomic orbitals? Yeah, this difference here is bond strength. You can go look it up in the back of your textbook. Those numbers come from this difference. Yep, did I see another hand? Yeah.
Are you able to partially fill it, and if you are, is that going to break it, or is that not?
Sure, can you partially fill it? Well, let's imagine we have an extra electron and we throw it into this hydrogen molecule. That may not, and the only place it can go is here. That would tend to cancel out about half of the bond. That would make the molecule kind of unstable, but it might not break the bond completely. Most of the stuff we do in this class is going to be about fully populating the antibonding orbital, so we won't worry about that too much. Okay, so filling an antibonding orbital breaks a bond. Now, with this in mind, last time we talked about the molecule ethylene, and we went through and identified where each of the bonds in ethylene come from, both sigma and pi. For example, we said that this sigma bond between carbon and hydrogen probably comes from overlap of a 1s orbital on hydrogen, and then what kind of atomic orbital on carbon? sp2. You know it's sp2 because that carbon is only surrounded by 3 groups, got to be trigonal planar, and so on. We went through that last time, okay? That's true for all of the carbon-hydrogen sigma bonds in this molecule. We talked about the carbon-carbon sigma bond between the 2 carbons. That's got to come from overlap of an sp2 on the first carbon with an sp2 on the second carbon. Now, how about the pi bond? Where did that come from? Which atomic orbital on carbon 1? It's the p orbital that's left over after we do the hybridization, right? So 2p orbital on one carbon plus the 2p orbital on the other carbon. Hopefully you can see in your mind by now the idea that those p orbitals, if I were to draw them here, are perpendicular to or orthogonal to the plane of the sigma bonds. They have to be, because we didn't use these p orbitals when we did the hybridization to generate the sp2 orbitals. And side by side, p orbital overlap looks like this, or alternatively, if you wanted to draw sort of a full pi bond, you could use a lobe that encompasses all of the space between the 2 nuclei. And of course, if you looked at it from the side, what you would see is that there is a lobe of this pi bonding orbital above the plane of the sigma bonds and another lobe below the plane of the sigma bonds. Now, all of that should make a lot of sense based on what we talked about in the study guide. The other thing we said last time is that sigma and pi bonds are not created equally. Which is higher in energy, sigma or pi? Pi. And the easiest explanation is simply that pi orbitals hold electrons farther away from the nucleus. That's a potential energy argument, okay? So with that in mind, we're now prepared to think about the energy diagram for ethylene. And based on what we talked about, you already know the answers. If we consider we'll draw energy on the y-axis, and then if you consider this dotted line here to be sort of the energy level of the starting atomic orbitals in this molecule, you can consider this as the break-even point. Anything below this dotted line are bonding orbitals, and anything above this dotted line are anti-bonding orbitals. Of course, at the line, those are atomic orbitals, and those would be orbitals that are not involved in bonding. So, if I were to rank the sigma bonding orbitals versus the pi bonding orbitals in this energy diagram, where should pi go relative to sigma? Above, right? So, and we don't need to draw this to scale. It doesn't need to be precise. We just need to know that the carbon-carbon pi bonding orbital is going to be higher in energy than all the sigma bonding orbitals. Now, if you want, we can count up the number of sigma bonds in the molecule. I see 4 carbon-hydrogen sigma bonding orbitals. They should all be identical. And then I see 1 carbon-carbon sigma bonding orbital. Now, those sigma bonding orbitals, carbon-hydrogen versus carbon-carbon, are not created equal. If you go look at bond strengths, a CH bond has a different bond strength than a CC bond. For our purposes, though, the difference between those two is entirely inconsequential. Because when we think about organic molecules, the most reactive electrons in the molecule are going to be the ones that matter. They're going to be the ones that participate in reactions. So we can sort of ignore the sigma bonds here because we know that the pi bond is higher in energy. Does that make sense? So you might be worrying, well, should I draw the carbon-carbon sigma bonding orbital a little higher or a little bit lower in energy than a carbon-hydrogen bonding orbital? There is an answer to that, and I don't care about it. And if I don't, then maybe you don't have to either, all right? So, yes, go ahead. So there are cases, and Nate's going to lead you through, I think, one example today of a time where a sigma bonding orbital is higher in energy than the other sigma bonding orbitals in the molecule. And that'll basically be the one time. So pay attention to that. But for the most part, if a pi bond is in the molecule, that's going to be higher in energy than any of the sigma bonds. So I'm going to use little, half arrows to indicate electrons paired in orbitals with opposite spin. Each orbital can take 2 electrons with opposite spin. There we go. Now, all of that's basically a repetition of what we've already learned and were saying before about sigma and pi bonds and their relative stability. Here's the new thing. The anti-bonding orbitals are essentially a reflection of the bonding orbitals. That is, if the pi orbital is higher in energy than the sigma bonding orbitals, then the pi star should be lower in energy than the sigma star anti-bonding orbitals. So I'll just show you real quick what a pi star anti-bonding orbital looks like. If we drew it from the side, it would look like this. It's essentially going to look like 2p orbitals side by side, but with opposite wave function sign and with a node in the middle. So this is what the pi star looks like. And I should have made those two about the same size, sorry. Opposite wave function sign, okay? With a dotted line, oops, in between them, you don't have to draw the dotted line. The node is obvious by the fact that the color changes as you go from left to right. But if you want to, you can draw the dotted line to indicate that is a node, okay? So automatically, go ahead.
When we're drawing things on a molecule that's given, for example, but it isn't a side view, do you still want us to draw it that way?
So if you're given a molecule and it's not drawn side view, how do you draw the pi star? You can either redraw the molecule side style, or you can do the top-down view, which would look like this. 2p orbitals side by side with a node in the middle, opposite wave function sign, like this. So it's just a matter of perspective, okay? Yes?
When we originally learned about molecular orbital theory, we learned that like with the anti-bonding orbitals, there's the two smaller lobes facing each other and the two larger ones
Right.
facing each other. So how does, I guess, trying to understand, connect the two, how does that work?
So what you're referring to really is what you see in a sigma star antibonding orbital. And this has to do with the difference between pi type overlap and sigma overlap. Remember, pi type overlap is simply side by side. Sigma type overlap is end on end. So when two p orbitals overlap side by side, you get something like this for the bonding orbital and this for the antibonding orbital. Let me just draw for you briefly what, let's just do the carbon-carbon sigma bond. The bonding orbital and the antibonding orbital, just so you can see what those would look like. So here is ethylene again. We're going to be focusing on the sigma bond. That carbon-carbon sigma bond comes from overlap of an sp2 orbital on one carbon with an sp2 orbital on the other, where the lobes in the middle are going to overlap with the same wave function sign. So that's going to look like this, and then there are going to be smaller lobes with nodes at the carbon pointing in the other direction. That's really what a sigma bonding orbital looks like. Now, how about the sigma star antibonding orbital between the two carbons? That's not much of an asterisk, I'm sorry. That comes from the out-of-phase combination of the two. Again, we'll take this sort of top-down view. In the sigma star antibonding orbital, there will be a node in between the two carbons with small lobes pointing at the node. Why are they small? Because the wave function has canceled itself out in the middle, and then larger lobes pointing out back 180 degrees away from the bond. So that's what a sigma star antibonding orbital looks like. Would you like to see the carbon hydrogen? Okay, it's not too hard. The carbon hydrogen bonding orbital, we'll just do this hydrogen here on the right, comes from overlap of an sp2 orbital on carbon with a 1s orbital on hydrogen. Essentially, this is going to look like an sp2 orbital on carbon that completely envelops the hydrogen. That's what you would get if you added the 1s orbital to the sp2 orbital. The antibonding orbital for that carbon-hydrogen bond, which you get from the out-of-phase or destructive interference combination of the two, has a node in between the two nuclei. It's got a lobe on the hydrogen that's leaning away from the node. Why is it leaning? Because we've canceled out electron density at the node. On the carbon, we're going to draw what essentially looks like an sp2 orbital backwards, the small lobe pointing towards the node and the large lobe pointing away from the node. Okay, that's what they look like. But essentially, that's just an intellectual curiosity, because if you go back to our energy diagram, the sigma stars are higher in energy than the pi star. So here's the jump, okay? In an organic molecule, the two most important orbitals are the highest energy filled orbital and the lowest energy empty orbital. We call those the frontier orbitals. And these are the ones that are going to be involved in any reactions, okay? So this highest energy orbital, that the pi orbital, we're going to call the highest occupied molecular orbital, the HOMO, and the pi star we're going to call the lowest unoccupied molecular orbital, the LUMO. Now get this, organic reactions usually involve a molecule with a high energy pair of electrons, a nucleophile, attacking an electrophile. And in organic chemistry, nucleophiles are the same as Lewis bases. You heard Lewis bases before, and you were told that a Lewis base is an electron pair donor. That didn't make any sense, because you're like, in what circumstance would this Lewis base start throwing electrons at somebody? That's actually the wrong image. The Lewis base is an electron donor because it has a high energy pair of electrons that it wants to share with another molecule so they can move lower in energy. You've also heard the term Lewis acid, and in organic chemistry, we're going to talk about electrophiles as Lewis acids. Electrophiles are electron lovers. Lewis acids are electron pair acceptors. And that doesn't mean that they're standing there waiting to catch a pair of electrons that somebody throws at them. That means they have a low energy empty orbital that they are willing to share with a high energy pair of electrons on another molecule to make a bond. And we will see that most bond forming reactions in organic chemistry involve the high energy occupied orbital on the nucleophile sharing electrons with or attacking the low energy empty orbital on the electrophile. Okay? So with that, my student Nate McMurray is now going to guide you through how to identify HOMO and LUMO in organic molecules, because that's going to be the key to potent predictive power in OChem. This is the first, I'm stealing Nate's line, this is the first and great commandment of OChem, that nucleophile attacks electrophile. And the second is like unto it. HOMO of the nucleophile attacks LUMO of the electrophile. All right, so Nate, come on down.
Hello, everybody. All right. So I think Dr. Price, in my opinion, may even be underselling it a little bit by calling it just the first great commandment. What we're learning today is essentially the entirety of OChem 1 and 2. And so if you understand what we're going through right now, like the class is pretty much done. After this, it's just semantics. And so if there is anything that is not really landing as we're teaching this, please stop us, ask questions. Because this is probably, if of all of the lectures we'll go through, this is probably the most important one to really have nailed down. So we're here talking about LUMOs and HOMOs, nucleophiles, electrophiles, and we obviously will want to know how to predict when we are encountering a HOMO or a LUMO, and how to predict which one is the Lewis acid, which one is the Lewis base, or which one is the electrophile, and which one is the nucleophile. So first, let's look at an example that you will, through your future intuition, see has a very, predictable HOMO and LUMO pairing. So if we look at a certain molecule, let's look at something like BH3. So a molecule like this, so boron, with its 3 bonds to hydrogens. So looking on the periodic table, boron is happy to make just 3 bonds, but it still has an empty p orbital. Sorry, not used to Apple products. So boron still has this empty p orbital that is just sitting there available for use. And if we look at its molecular orbital diagram, very roughly, it's going to have its sigma bonds, its BH sigma bonds, and its BH sigma star bonds, or antibonds. And then in the middle, we're going to have this unhybridized, unused p orbital. So just the p orbital of the boron. Just, again, sitting there, not doing anything, completely empty and devoid of electrons. If we populate our electrons, we know boron comes with 3 electrons, hydrogen comes with 3 electrons. So we've got 6 electrons to dump into this molecular orbital diagram. So we've got 1, 2, 3, 4, 5, 6. So we see those sigma bond, or those sigma orbitals completely filled. Again, that p orbital completely unfilled. Now, if we have something come along with electrons sitting above that p orbital, that's an indication that we can see a reaction. So if we have some nucleophile where we've got electrons up here, so let's just call that Nu for nucleophile, we can see a reaction where these electrons want to dump down into a lower energy orbital. And so from a diagram point of view, that's what that's going to look like. So then, when we see that in our molecule, we're going to see just that. We're going to have some nucleophile with a lone pair come in, dump its electrons into that empty p orbital, and we'll see a chemical reaction. We'll see a bond form in that way. So just as like a primer to the idea, how is that sitting with us? Have I lost anybody yet? Yeah?
I'm kind of confused on the FDP orbital. So is it considered a bonding or anti-bonding orbital? Yeah.
So good question. So is the p orbital, is it considered a bonding orbital or an anti-bonding orbital? The answer is actually neither. So if we look at that sort of break-even line, this p orbital sits exactly on that break-even line. Because that break-even line we were talking about, that's what we're saying, as we create our bonding and our anti-bonding orbitals, where are we moving from? How much is our anti-bonding orbital going above? How much is our bonding orbital going below where it used to be, its native state? So this p orbital, it wasn't hybridized. It wasn't used. There's no electrons. It's not involved in any bond originally. And so it's sitting just exactly in the middle, exactly on, again, as we called it, the break-even line. Does that make sense? Okay. Yeah, let's go back here and then I'll come back.
So is boron stable with 4 bonds?
We will see some fun chemistry with it in the future. So just using it as a first example as something just with an empty p orbital. But we'll see it does behave as a very good Lewis acid, a very good dump of electrons.
Nate, do you want to draw the product that would form from attack of that generic nucleophile onto pH3?
Yeah, so if we saw that, so the product that we would get would be simply where we have the boron, we're bonded to still our 3 hydrogens, and then we've simply created a bond to our nucleophile. In this case, it would leave a positive charge on the boron, just for correctness sake. Or negative, sorry, yes, negative. Let's see, there we go, yes, a negative charge on the boron, my bad.
I don't like this, I'm heckling.
But yeah, sorry, let's go here.
Would the nucleophile always have an available lone pair for bonding? Is that like a rule?
Essentially, yes. So as we mentioned, we have some orbital, just some orbital filled with electrons that want to find somewhere else to go. Essentially, electrons are jealous. So electrons are very jealous. Anytime they see somewhere they can go, they will try to go there. And so a nucleophile needs to have some electrons in a high energy orbital, in a high energy HOMO orbital. And if they start side-eyeing a LUMO that's available, we're going to see that reaction occur, given the right conditions. And so yes, so a LUMO or a nucleophile does need to have those electrons for this to occur. Yeah?
So for the p orbital that's just empty, like when you're drawing it, does it have shading to it like an hybridized?
It would.
Okay.
Yeah, I'm just being lazy here, but yes, it would still have its shading.
On the diagram, how do you tell that apart from just like a pi orbital if you're drawing them both?
So, good question. So, we'll come back to that in a moment. We'll look at a molecule with some more interesting features. I would say for the most part, a pi orbital, you're going to be sharing an orbital with another atom, where in here this p orbital is completely isolated. It's just stuck on that boron. It's not being shared with another atom. And so I think that's kind of the main ways. There's kind of context clues.
Do you guys know how to tell that empty p orbital is there? I mean, here's the reasoning, right? Boron is trigonal planar because it's only surrounded by 3 groups. You can tell because if there was a lone pair there, it would have a formal charge on it, and it doesn't. Follow that reasoning? So then, because it's only surrounded by 3 groups, it's got to be trigonal planar. You explain each of the sigma bonds with an sp2 orbital. And so what you've got left is that unhybridized p orbital that has no electron pair.
Yeah. Yeah.
So in terms of HOMO and LUMO, would the HOMO be the p orbital on the borons?
So the LUMO. So remember what they stand for. So lowest unoccupied molecular orbital. So that's the target. That's where electrons want to move. Where the HOMO, the highest occupied molecular orbital, that would be the nucleophile. So where the electrons are coming from, where the occupied place. Yeah.
Is boron going to be the only atom that we're looking at that has this empty unhybridized p orbital?
Absolutely not.
What
No.
other ones would look like this?
We'll see plenty. We'll talk about some. So yeah, as we're going through, we will answer that question thoroughly, and then.
How do we know how many orbitals a given atom has?
So remember back to Chem 105, 106. So the way the periodic table is arranged, those first 2 columns are the s block. Those have 1 s orbital. The next block, the boron, carbon, nitrogen, oxygen, fluorine, neon, that's the p block. And all of those have 3 p orbitals, per row. And so the answer is actually just that. So every atom has an s orbital and 3 p orbitals. Now, whether or not those are populated depends on how many electrons it has. But, boron, just because it only has 3 valence electrons, 2 of those being in the s orbital natively, doesn't mean those other p orbitals don't exist. They're just not populated. It's a very good question. Okay, let's take one more and then we'll probably answer some more questions as we go through some stuff.
If every atom has a HOMO and every atom has a LUMO, and the HOMO is typically lower in energy than the LUMO, how do we know if the reaction's actually going to occur?
So therein is essentially the rest of organic chemistry, is when do we decide when the HOMO is important and when the LUMO is important. So that one I'll say, stand by for the rest of the semester. We'll talk about some examples today. I won't leave you completely hanging. We have a few kind of general rules we can use to from a surface level point of view, say oh yeah, this is probably an important orbital, or it's probably not that important. So we'll get to that.
I'll interject though just briefly to say that for the nucleophile, what we care about is the HOMO, the highest energy electrons. We don't really care about the LUMO, the nucleophile, because the nucleophile is going to be the reactive one with the high energy pair of electrons that does the attacking. Similarly for the electrophile, we don't really care about the HOMO, we care about what is the lowest energy place electrons could go. So always HOMO the nucleophile, LUMO the electrophile. Second thing is the reason nucleophiles are jealous and or want to share electrons with an empty orbital is because doing so, bonding always lowers the electrons in energy. So this isn't random, it's just that by sharing electrons, they move lower in energy. When a nucleophile attacks an electrophile, the electrons in that boron nucleophile bond are lower in energy than they were when they were in a non-bonding orbital on the nucleophile.
Okay. Yeah. Thank you. Now, dumb question. How do I make a new page?
Up to the,
Is that
I don't
this
know.
one? I actually don't know. Again, I'm a Samsung guy. I don't know how to do this.
Probably this.
Oh,
and
there we go.
then add page.
Okay, perfect. Okay. Next lecture we'll think I'm competent at this. Okay. So now let's run through what we want to look for. Again, kind of at a surface level. We'll learn, deeper semantics as we go through the semester. But for right now, what we want you to understand, let's talk about how to identify an important LUMO and an important HOMO. So starting with that HOMO. So for a HOMO, we want to look for kind of two main things. First, a lone pair. So lone pair electrons, as we saw in the boron example here, those stand on that break-even line. And very commonly in a molecule, when we create that bond, well, actually always when we create that bond, the electrons are going to drop in energy. And so it would just make sense that if we're looking at everything that went down and everything that didn't move, the highest things would be what didn't move. So in the boron example, with that nucleophile, we have, with the boron, so we have that p orbital accepting that lone pair where that was available. We'll look at some examples of that in a moment. But lone pairs are very, very attractive candidates for a HOMO. If you're looking at something you've never seen before, those are common. Second is going to be pi bonds. So we'll see through the semester that pi bonds are pretty reactive. So molecules that have pi bonds in them like to do chemistry. The reason for that is because pi electrons are higher in energy than sigma electrons. And so if we're in a situation where there's no lone pairs, but we see a pi bond, that pi bond is almost always going to be the source of our chemistry. Again, simply the reason being, pi bonds aren't as stabilized. They're higher in energy. So lone pairs and pi bonds tend to be our HOMOs. If we see something else, so if we see some other source of electrons, we simply don't really care. So it doesn't matter. So you can brute force some calculations, you can run some expensive algorithms, and you can find in some massive molecule what the exact HOMO is. But if it's honestly not a lone pair or a pi bond, it's not going to do anything significant. If we have 1,000 sigma bonds in our massive molecule, they're all pretty much the same. Sure, you can maybe make some fancy predictions, but you're not going to achieve anything significant. So moving on, that's what we're looking for, is just those two things mostly.
What about when it spawns to chlorine, or halogens?
So when we talk about LUMOs, so give that a moment.
But actually, it's a good question. Like, how do you rank lone pairs if you have multiple lone pairs? And that's what chapter 2 is actually all about. We're going to learn to rank how reactive lone pairs are.
Yeah.
So when you say it doesn't matter, are you just saying that it won't, we're not even going to look at those?
Yeah, because if it doesn't perform chemistry, does the chemist really care that much? Some chemists, sure. But if I'm trying to achieve a chemical reaction and I see, some sigma electrons that are a little bit higher in energy than the rest of the sigma electrons, nothing's going to happen in my test tube. And so I'm not super interested in it. Now, sure, if you go deeper into organic chemistry, we'll see some stuff. But as far as this class goes, and especially as far as this chapter and this test goes, this is what we care about, is just these two things. Yeah?
So if it asks for the HOMO molecule that only has sigma bonds, do we just say it doesn't matter?
If it's asking what is the HOMO, you'd say, well, it's a sigma bond. It's one of the sigma bonds. But we couldn't ask you a question like, oh, what's going to happen if we mix these two chemicals if the HOMO is essentially a contest between 20 different orbitals. So, okay. So now with LUMOs, so a lowest unoccupied molecular orbital, the things that we're looking for are the following. First, an empty p orbital. So an empty p orbital is a very strong candidate to be a LUMO. So again, it's unoccupied, lowest unoccupied molecular orbital. So if we see something like in the boron, or some other examples that we'll see, it just has a p orbital sitting there. It's high in energy, and a very good just kind of location for electrons to dump into, or lower in energy, I should say. So an empty p orbital, something we're looking for as a LUMO. Second, we can look for a pi star orbital. So pi star orbitals, likewise, since pi orbitals tend to decrease in energy compared to the break-even point, but not as significantly compared to the sigma, it would make sense that it's going to raise in energy, the antibonding orbital, less significantly, less dramatically than the sigma star. So if we're just concerned about these frontier orbitals, we just care about what's the immediate lowest LUMO, the lowest unoccupied orbital, it's going to be that pi star. Third, we can look for sigma stars if we have a halogen bond. So X is commonly used in organic chemistry to mean a halogen. So that's fluorine, chlorine, bromine, iodine. So if we have a bond to a halogen, that sigma star bond is going to be significantly different in energy compared to the other sigma bonds, and it's a good candidate, again, for being a LUMO. Now, beyond that, we once again don't care. So again, you can brute force some calculations, maybe find what the LUMO is, but if it's not one of these three things, it's not going to be significant for our purposes. Yeah?
So if a molecule has a pi bond, it's going to also have an anti-pi orbital. How can we tell if it's going to be considered a HOMO or a LUMO?
Yeah, so the pi bond usually is going to be that HOMO, because that's where the electrons are. You can't be a LUMO if you're occupied. That violates the acronym. Now, our pi star, for the most part, pi stars are going to be empty of electrons because they're all in the bonding orbital. And so that's going to be a candidate for the LUMO. So we can pretty much say with certainty that if it's a pi bond, it's going to be a HOMO candidate, while a pi star is going to be a LUMO candidate. And we're not really going to see examples where that's going to, confuse with each other.
I guess follow up that if it has a pi bond, then it's also probably going to have an empty pi star orbital.
It will always have an empty pi star orbital.
Okay, so
Every bonding orbital has a corresponding anti-bonding orbital. You will never see just a sigma orbital. There will always be a sigma star that complements it.
But remember, though every molecule has a HOMO and a LUMO, you only care about the HOMO for nucleophiles, and you only care about the LUMO for electrophiles. Right now, you probably don't know how to identify a nucleophile from an electrophile, and that's okay. We're going to help you with that. But pretty soon you'll get it.
Yep. Yeah.
So you can fill a pi star orbital without breaking it, and you can also do that for sigma star orbital if it's bonded to a halogen.
So good question. So we don't want to necessarily say that we can fill these antibonding orbitals. So what will happen is if we have a bonding orbital that's filled, and we have a corresponding antibonding orbital that's filled, that creates a broken bond.
For either pi or
Yep. So if the pi stars, or if the pi orbital's partner, the pi star gets filled, that pi bond has broken. If that sigma's corresponding sigma star has been filled, then the molecule, that bond will be broken. And that's what we see some of those on the problem set. And we'll see if I can blast through this material and show what that looks like. Yeah, real quick.
yeah, whenever we're trying to identify the HOMO and LUMO, would there ever be any situations where there's like an empty orbital and a pi star orbital?
Of course there could be. Yeah. So now we can sort of consider this more or less like a ranked list. So an empty p orbital is usually going to be lower in energy because it's at the break-even point compared to a pi star. But absolutely, we can see a molecule that has a p orbital and an antibonding pi orbital. But that p orbital is usually going to be lower in energy. It's that frontier. It's incorrect to call it this, but some students like calling it a valence orbital. You know, just like with valence electrons, they're the only ones we care about. We don't care about the other electrons. So here, like, we don't care about any of the orbitals that are way up or way down. We just care what's right at the boundary.
Do you see what he's saying? That if an empty p orbital is present, it's necessarily lower in energy than the pi star because it's not been involved in bonding. So you find the lowest empty orbital, and then you don't care about the other empty orbitals.
Yeah. Okay. So if we look at the quiz, so question 2 asks you to draw a LUMO, write the name of a LUMO. So if we look at something like this, so
The quiz is actually up there if you wanted to scroll to the
Oh,
next
yeah.
page.
yeah, let's just look at this together. So yeah, so the molecule shown below is an example of an electrophile or Lewis acid. Write the name of the LUMO of this electrophile. Then draw the LUMO on the molecule using shading as appropriate to indicate orbital phase. So we just learned that an important LUMO is first a p orbital, next a pi star orbital, and then next halogens. So looking at this molecule, I don't see any p orbitals. And this is the process I would go through to find this. So I don't see any empty p orbitals. You know, everything is involved in a bond. My oxygen is tetrahedral, or trigonal planar, excuse me. So it's got its lone pairs there and hybridized orbitals. Its p orbital that it has remaining is involved in a pi bond. So no empty p orbitals. Likewise, that carbon is doing the same thing. And then here we have our CH3, our CH3. Those aren't really doing anything interesting. So no empty p orbitals, but I do have a pi bond. So if I have a pi bond, that means I have a pi star. So the LUMO, is going to be my pi star between my carbon and my oxygen. And again, that's just looking at our list, our kind of ranked list of priorities. So again, because there's no empty p orbital, and there's no halogens to care about, though that's lower in the list anyways, yeah?
Shouldn't there be an empty p orbital along central carbon because it's only got two hybridized?
So that p orbital is part of the pi bond. So if we look at this, let's kind of, so our p orbitals that we would have, again, are involved in bonds. So, you know, if that oxygen wasn't there, if that double bond wasn't there, then, you know, sure, there absolutely could be an empty p orbital. And we'll see lots of carbons that do that. But that's probably a poor drawing of that. Yeah, so between the carbon and the oxygen, again, so we've got these p orbitals, and those are involved in the bond, so that pi bond. It's a double bond. So there's 1 sigma, 1 pi, creating that bond. And so that would be the HOMO, what we just drew. So the LUMO, we want to draw a pi star. So we're drawing this orbital with a node in the middle, and we would draw that accordingly. So the answer to this question would be that antibonding pi orbital. And so again, we just looked at that list that we had and acted accordingly.
So my intent for these quizzes is that you would turn them in, but we haven't hardly done any of this. So what do you guys want to do? I mean, you can put your name on them and turn them in and get credit for time served, or you can wait till Friday, and then we can turn them in Friday. What's best? Friday. I think Friday. You want Friday? Okay.